Hello everyone. Welcome to my YouTube channel on engineering mathematics. In this video, we are going to see third application of de Moivre's theorem, that is to find nth roots of the complex number. Finding nth roots of the complex number x plus iy is equivalent to solve equation z raised to n minus x plus iy is equal to 0. Since this is degree n equation, it will have n distinct roots. Therefore, note that any complex number x plus iy will always possess n distinct nth roots. Now let us see method to find nth roots of complex numbers. This method consists of 3 steps. In step 1, we will find the polar form of complex number z. Say it is r into cos x plus I sin x. Then nth root of z, that is z raised to 1 by n, will be equal to r raised to 1 by n into cos x plus I sin x whole raised to 1 by n. Now in step 2, we use relation cos of 2k pi plus x is equal to cos x and sine of 2k pi plus x is equal to sin x. This relation is due to periodicness of cosine and sine functions. Both cosine and sine functions are periodic of period 2 pi. So this relations holds. So after substituting these relations in above equation, we get z raised to 1 by n is equal to r raised to 1 by n into cos of 2k pi plus x plus I sin 2k pi plus x whole raised to 1 by n. Note that k is any integer. Now, by de Moivre's theorem, we can write this statement as r raised to 1 by n into cos of 2k pi plus x upon n plus I into sine of 2k pi plus x upon n. Note that we have multiplied these angles with this degree 1 by n. This is due to de Moivre's theorem. Now here at this point we say k varies from 0 to n minus 1. In the beginning I said k is any integer. Now I am saying k takes values from 0 to n minus 1. In fact, k take all the integer values, but for these values of k, z takes distinct values. Now finally in step 3, we substitute one by one these values of k in this statement to get n distinct roots of z. Now let me show you some real examples. In this example, we are asked to find values of minus I raised to 1 by 3. That means we have to find cube root of minus I. So here our complex number is z is equal to minus I. According to step 1, we have to write polar form of this complex number. So let us first find out modulus and argument of this complex number minus I. Modulus of z, that is modulus of minus I, will be 1. And since minus I lies in 4th quadrant, its argument can be given by 2 pi minus tan inverse of 1 by 0, which is 2 pi minus pi by 2, that is 3 pi by 2. Therefore, polar form of z is equal to minus I is cos of 3 pi by 2 plus I sin 3 pi by 2. So minus I raised to 1 by 3 is cos 3 pi by 2 plus I sin 3 pi by 2 whole raised to 1 by 3. Here we complete the first step. Now according to second step, we have to use the relation cos of 2k pi plus x is equal to cos of x and sine of 2k pi plus x is equal to sine of x. So after replacing this cosine and sine function, we get cos of 2k pi plus 3 pi by 2 plus I sin 2k pi plus 3 pi by 2 whole raised to 1 by 3. Now we apply de Moivre's theorem, according to which we get cos of 2k pi plus 3 pi by 2 divided by 3 plus I sin 2k pi plus 3 pi by 2 divided by 3. Here we say that k takes values from 0 to n minus 1. Here n is 3, so n minus 1 is 2. So k takes values 0, 1 and 2. Now we are finally in step 3. We have to substitute these values of k one by one in this statement to find out n distinct roots of this given complex number. So when I put k is equal to 0 over here, I get my first root. I label it as x naught. When I put k is equal to 1, I'll get my second root. I'll label it as x1. Similarly, when I put k is equal to 2, I'll get my third root. I'll label it as x2. So x0 will be cos of 3 pi by 2 by 3 plus I sine 3 pi by 2 by 3. That is cos of 3 pi by 6 plus I sine 3 pi by 6, which is same as e raised to I 3 pi by 6. Now let's substitute k is equal to 1 over here. We get x1 is equal to cos of 7 pi by 6 plus I sine 7 pi by 6, which is e raised to I 7 pi by 6. And finally, we put k is equal to 2 over here. We get x2 is equal to cos of 11 pi by 6 plus I sine 11 pi by 6, which is same as e raised to I 11 pi by 6. So here values of minus I raised to 1 by 3 are e raised to I 3 pi by 6, e raised to I 7 pi by 6 and e raised to I 11 pi by 6. I hope guys you understood how we found this solution. Now let us proceed for example number 2. Here we are asked to solve equation x raised to 6 plus 1 is equal to 0, and we are asked to find the continued product of all the roots of this equation. Since this is degree 6 equation, it will have 6 distinct roots. So let's find them all. Consider the equation x raised to 6 plus 1 is equal to 0. This equation can be written as x raised to 6 is equal to minus 1, which is same as x is equal to minus 1 raised to 1 by 6. Now we have to find out 6th root of minus 1. We consider here given complex number is minus 1. Now according to first step, we will write its polar form. Polar form of minus 1 is cos pi plus I sin pi. So minus 1 raised to 1 by 6 is cos pi plus I sin pi whole raised to 1 by 6. Now according to step 2, we will use the relation cos 2k pi plus x is equal to cos x and sin 2k pi plus x is equal to sin x, and we write this equation as x is equal to cos of 2k pi plus I sin 2k pi plus pi whole raised to 1 by 6. Then by de Moivre's theorem, this RHS can be written as cos of 2k pi plus pi whole divided by 6 plus I sin 2k pi plus pi by 6. Here we say k takes values from 0 to n minus 1. Since n is 6, n minus 1 will be 5. So k takes values 0, 1, 2, 3, 4 and 5. Now according to step 3, we will put values of k one by one in this equation and we will find out 6 distinct roots of this. So when I put k is equal to 0, I get x is equal to cos of pi by 6 plus I sin pi by 6, that is e raised to I pi by 6. When we put k is equal to 1 over here, we get cos of 3 pi by 6 plus I sin 3 pi by 6, that is e raised to I 3 pi by 6. Now let's put k is equal to 2. We get x is equal to cos of 5 pi by 6 plus I sin 5 pi by 6, that is e raised to I 5 pi by 6. Substituting k is equal to 3, we get x is equal to cos of 7 pi by 6 plus I sin 7 pi by 6 is equal to e raised to I 7 pi by 6. Now let's put k is equal to 4. We get x is equal to cos of 9 pi by 6 plus I sin 9 pi by 6, which is e raised to I 9 pi by 6. Finally, when we put k is equal to 5 over here, we get x is equal to cos of 11 pi by 6 plus I sin 11 pi by 6, that is e raised to I 11 pi by 6. These are all n distinct roots of the given equation. Now we are asked to find the continued product of all these roots. So let us multiply these roots. So after finding continued product of these roots, we get e raised to I into pi into 36 by 6. We have simply added these powers. But 36 by 6 is 6. So this will become e raised to I 6 pi, which is same as cos 6 pi plus I sin 6 pi, which is 1. Because cos 6 pi is 1 and sin 6 pi is 0. So continued product of all the roots of this equation is 1. I hope guys you understood this solution. Now let us proceed for next example. Here we are asked to find all the cube roots of unity. Unity means 1. This same question can be asked like solve equation x cube minus 1 is equal to 0. So if we take this equation x cube minus 1 is equal to 0, it can be written as x cube is equal to 1. Therefore, x is equal to cube root of unity. Now here complex number is 1. Then its polar form will be cos of 0 plus I sin 0. So cube root of 1 is cos 0 plus I sin 0 raised to 1 by 3. Now according to step 2, we can write this statement as cos of 2k pi plus 0 plus I sin 2k pi plus 0 whole raised to 1 by 3. You can neglect writing this 0. Then by de Moivre's theorem, we can write this as cos of 2k pi by 3 plus I sin 2k pi by 3, where k takes values 0 to n minus 1, that is 0 to 2. Now let us substitute values of k one by one into this to find out 3 distinct roots of this equation. So when I put k is equal to 0 here, I'll get cos 0 plus I sin 0, that is e raised to I 0, that is 1. When we put k is equal to 1 over here, we get cos of 2 pi by 3 plus I sin 2 pi by 3, that is e raised to I 2 pi by 3. And lastly, when we put k is equal to 2, we get x is equal to cos of 4 pi by 3 plus I sin 4 pi by 3, that is e raised to I 4 pi by 3. These are 3 distinct roots or cube roots of unity. Let us go ahead for example number 4. Here we are asked to solve this degree 7 equation x raised to 7 plus x raised to 4 plus I into x cube plus 1 is equal to 0. Let us consider this equation. I see that x raised to 4 is common in first two terms. So if we take it out, we will get x cube plus 1 inside the bracket. Now once again we have a common term x cube plus 1. So when we take it out, we get x raised to 4 plus I inside the bracket. Now we have factors x raised to 4 plus 1 and x cube plus 1 of this expression. So either this x raised to 4 plus I is equal to 0 or x cube plus 1 is equal to 0. When we take x cube plus 1 is equal to 0, we get x is equal to minus 1 raised to 1 by 3. And when we take x raised to 4 plus I is equal to 0, we get x is equal to minus I raised to 1 by 4. Now let us tackle one by one these equations. When we take x is equal to minus 1 raised to 1 by 3, polar form of minus 1 can be written as cos pi plus I sin pi. Later, according to step 2, this can be written as cos of 2k pi plus I sin 2k pi plus pi. Then by de Moivre's theorem, this can be written as cos of 2k pi plus pi by 3 plus I sin 2k pi plus pi by 3, where k varies from 0 to 2 because n is 3. Now let us take another equation, x is equal to minus I raised to 1 by 4. Here complex number is minus I. Its polar form will be cos pi by 2 minus I sin pi by 2. So minus I raised to 1 by 4 is cos pi by 2 minus I sin pi by 2 whole raised to 1 by 4. According to step 2, we will replace cosine and sine by cos 2k pi plus x minus I sin 2k pi plus x. Then by de Moivre's theorem, this statement can be written as cos of 2k pi plus pi by 2 by 4 minus I sin 2k pi plus pi by 2 by 4, where k takes values from 0 to n minus 1. Here n is 4. Now when we substitute these values of k over here and these values of k over here, we will get 7 distinct roots for this equation. I'm leaving that part for you guys. Okay, now let us go ahead for last example of this video. Here we are given if alpha, alpha square, alpha cube and alpha raised to 4 are the roots of the equation x raised to 5 minus 1 is equal to 0, then we have to prove that 1 minus alpha into 1 minus alpha square into 1 minus alpha cube into 1 minus alpha raised to 4 is equal to 5. So here there are two parts in the question. In first part, we have to find out roots of x raised to 5 minus 1 is equal to 0 equation, and then we have to prove this equation. So let us first find out those roots. We consider the equation x raised to 5 minus 1 is equal to 0. It can be written as x is equal to 1 raised to 1 by 5. So here we have to find out fifth roots of unity, that is 1. So complex number is 1 here. Its polar form is cos 0 plus I sin 0. According to step 2, we can write this as cos of 2k pi plus I sin 2k pi whole raised to 1 by 5. Then by de Moivre's theorem, this can be written as cos of 2k pi by 5 plus I sin 2k pi by 5, where k takes values from 0 to 4. Now let us substitute one by one these values of k over here to find those 5 distinct roots. So when I put k is equal to 0, I get a root as x0 is equal to cos 0 plus I sin 0, that is e raised to I0, which is nothing but 1. Now let's put k is equal to 1 over here. We will get cos of 2 pi by 5 plus I sin 2 pi by 5, that is e raised to I 2 pi by 5. Similarly, we will put k is equal to 2, 3 and 4. When we do so, we will get roots x2 is equal to e raised to I 4 pi by 5, x3 is equal to e raised to I 6 pi by 5, and x4 is equal to e raised to I 8 pi by 5 respectively. So roots of x raised to 5 minus 1 is equal to 0 are 1 e raised to I 2 pi by 5, e raised to I 4 pi by 5, e raised to I 6 pi by 5, and e raised to I 8 pi by 5. But in the question it is given that alpha, alpha square, alpha cube and alpha raised to 4 are the roots of the equation x raised to 5 minus 1 is equal to 0. So which one among these 5 roots is your alpha, alpha square, alpha cube and alpha raised to 4? So to find out these alphas, you have to look these roots closely. Come on, guess which one of these, if we take as alpha, you will get alpha square over here itself, alpha cube, alpha raised to 4 over here itself. Yes, you are correct. We should take alpha is equal to e raised to I 2 pi by 5. So if we let alpha is equal to e raised to I 2 pi by 5, alpha square will be e raised to I 4 pi by 5. Alpha cube will be e raised to I 6 pi by 5, and alpha raised to 4 is equal to e raised to I 8 pi by 5. Now finally we got all our alphas. Now we can say roots of equation x raised to 5 minus 1 is equal to 0 are 1, alpha, alpha square, alpha cube and alpha raised to 4. Since these are the roots of the equation x raised to 5 minus 1 is equal to 0, we can factorize x raised to 5 minus 1 as this: x minus 1, x minus alpha into x minus alpha square into x minus alpha cube into x minus alpha raised to 4. We label this as equation number 1. We do have another factorization for x raised to 5 minus 1, which is x raised to 5 minus 1 is equal to x minus 1 into x raised to 4 plus x cube plus x square plus x plus 1. We label it as equation number 2. Now observe equation 1 and 2. Their LHS are same, so their RHS has to be same. So after comparing equation 1 and 2, we can say these two RHS are equal. Now from these two RHS, this x minus 1 and x minus 1 will get cancelled. We end up with this new equation. Now in this new equation, if I put x is equal to 1, on LHS side we will get 1 plus 1 plus 1 plus 1 plus 1 5 times. So this is nothing but 5. And on RHS we will get 1 minus alpha into 1 minus alpha square into 1 minus alpha cube into 1 minus alpha raised to 4. So ultimately we see that 1 minus alpha into 1 minus alpha square into 1 minus alpha cube into 1 minus alpha raised to 4 is equal to 5, which is the required answer. I hope guys you understood all the questions and their solutions I discussed in this video. In my next video, I'll be talking about the introduction of hyperbolic functions and their identities. Till then, Keep watching my videos. Thank you all of you. Thank you for watching this video. Please subscribe my YouTube channel and press the bell icon to get updates about my new videos.